I recommend that you start on working on the motor this week. The equipment that's needed to test them is already set up, so you can come anytime during the week and test your motors. All right. Also, you have the lab to work on. I'm not going to have any more worksheets for you guys the rest of the semester. It's basically after this chapter 31 homework, there's only 3 more web assigns, and really that's it. And so you can try focusing on the next 2 labs. Okay. So what I'm going to do is basically finish chapter 31, talk about motional EMF and some applications of Faraday's law. So the other day, I finished off introducing what motional EMF was. So let me briefly go over that again. You have a rod, on a conducting rod, on a set of conducting rails. Let's pretend there's no friction in between the conducting rod and the rails. And let's just, for the time being, say I gave it some initial velocity. I just give it a push. And we said that since there's charges in this rod and the charges are moving in this magnetic field, the negative and positive charges are going to separate in this rod until the electric field that's induced due to the motion of the rod, or the force on the charge due to the electric field, is equal and opposite to the force on the charge due to the magnetic field. And since the magnetic field is uniform, then the electric field would be uniform. And we were able to calculate the potential difference across this rod. We call that potential difference the motional EMF. And it's easy to calculate, just B times L times V. And so really what's happening here is the flux is changing. And we'd say another way the flux can change. It can either change because the circuit is changing, or because of the fact that the magnetic field is changing. So I wrote it up here. Okay, I wrote this in terms of 2 different types of EMFs that can be induced. One because the magnetic field is changing, and the other one because the circuit is moving. Okay, so there's a motional part and an induced part, but they both involve a time rate of change of flux. We also talked about the direction of the induced current, because we said that the force on the electrons the other day in this particular scenario was downward. And so you would get a separation of charge, positive here, negative here. And that would mean that there's a current flowing counterclockwise. Okay? Now what does that mean now that there's a counterclockwise current? Well, oops, 1 second. It means you have a rod carrying a current that's in a magnetic field. And so this rod will experience a force. Now, can we reason out without using IL cross B, what is the direction of the force on this rod? Is it going to be to the right or to the left? What do you think? Without using IL cross B.
Would it be to the right?
Well, okay, so let's think about that. If the force is to the right, so if the force is in that direction, what's rod going to do? Speed up or slow down?
accelerate to the right.
Accelerate to the right. Where's the energy coming from?
The energy of your push or the energy to the field?
The applied force.
Well, remember what I said was I gave it a push and let it go. So if I'm not touching it, where's the energy coming from?
Not from the field.
It's what?
It's not from the field. The field can't do work.
The field can't do work. Okay, so my point is that if it goes to the right, we're going to violate conservation of energy because there's nothing making it go to the right. Okay? So I just gave it a shove and let it go. There's going to be a force to the right, you're saying. That means it's going to accelerate. It would be nice if that would happen, though, because then we can get more out than we put in. That would violate law of conservation of energy. So it doesn't, the force is not to the right, it's really to the left. It has to be to the left. The force on this rod, as a result of this induced current, has to be to the left. It has to want to slow this down. Okay? Well, let's use the right-hand rule now to prove what I said. Okay, so if the current's going counterclockwise, then in the rod, the current's going this way, the magnetic field's into the board. The right-hand rule says that the force is to the left. It has to be that way. Because if it went to the right, we would violate the law of conservation of energy. We would get more out than we put in.
Which right-hand rule was that?
I'm sorry?
Which right-hand rule?
I put my fingers in the direction of the current and curl them towards the magnetic field. Okay? Because remember, F for a rod is I, L cross B. So it's the same right-hand rule as for a charge in the magnetic field. Okay? All right, so there's a current running in here. The current, if this is the voltage, the current in the circuit is going to be B, L, V rod over the resistance of whatever I have in my circuit. And the force on it, the magnitude, and I'm not going to write this as a vector. I know that L and B are perpendicular to each other. So the magnitude of F is I, LB. So it's going to be my induced current over R times the length of the rod times B. So that's the force in the rod, and it's to the left. Okay. Now, is there another way I can derive this? Sure. And I'm going to do that now. Okay. So let's assume I'm not, it's slowing down. Okay. Now, there's a current in this circuit. As long as this rod is moving, there's a current in this circuit. Where is the energy dissipated by the resistance coming from? Well, it comes from the kinetic energy of the rod. So there's current in the circuit, and it comes at the expense of the kinetic energy of the rod, so it slows down. We can calculate the power dissipated by my circuit, which is going to be delta V times I. Or you can write it as I squared R, however you want to write it. And so this is going to be B times L times V of the rod times B times L V of the rod over the resistance. This comes out to be B squared L squared V rod squared over R. So this is the power dissipated by that circuit. It's probably a small number. We'll put some numbers in a minute. But that's what it is. Do you remember an equation between power and force in Physics 205? Don't remember? Power is the time rate of change of work, right? In Physics 205, you learned that power is force times velocity. And in this case, it's the velocity of the rod. So we can solve for the force. All I got to do is divide by the velocity of the rod. And I get the matching expression. So these agree, they have to. Okay. Questions about what I've done so far? No questions? Yeah. So let's put in some numbers. Let's let B equals 0.8 Tesla. Let's let V equal 5 meters per second. And let's L be 1.6 meters. So in this particular case, delta V is going to be 0.8 Tesla times 5 meters per second times 1.6 meters. And that comes out to 6.4 volts. So the induced EMF is 6.4 volts. My current is going to be 6.4 volts over R. Let's say R is 96 ohms. This gives us a current of 0.067 amps. And our power, if you multiply this times that, our power is 0.43 watts. And after a minute, you've used up 26 joules of energy at the expense of the kinetic energy of the rod. So the rod, if I just let it go, it's going to lose 26 joules of energy. Okay. Questions on this?
Yeah, I'm sorry. Can you repeat that last thing that you said? The energy.
Well,
energy used.
because the circuit used up 26 joules in a minute, because you take 0.43 watts times 60 seconds, that gives you 26 joules. That energy came from the kinetic energy of the rod. So the rod loses a kinetic energy of 26 joules.
Okay, thank you.
Okay. If I wanted to keep the rod moving at a constant velocity, I'd have to apply a force equal to whatever this is. Okay? So this force is basically going to be 0.43 watts times my velocity. That'll be the force. That's the force I have to apply to keep this thing moving at a constant speed. Okay, otherwise it's just going to eventually come to a stop. And I'm going to solve the problem. I'm going to solve the problem where I'm going to look at the velocity of this as a function of time. I just give it a push, and let's see what happens. When does it come to a stop? I'll do that problem later today. Okay. Now, the direction of the current that's induced in this circuit is consistent with the law of conservation of energy and Lenz's law. All right? The direction of the current, again, if it was the other direction, this thing would accelerate. Okay? All right. So what is Lenz's law? Lenz's law states that the induced current opposes the change in flux. In fact, in this particular case, the induced current produced a force that opposes the motion of the rod. Okay? In this particular case, it produced a force that opposed the motion of the rod. Let me go back one. So let me say a little bit more about Lenz's law. Lenz's law says that the induced current, saying it in more general terms, opposes the change in flux. What does that mean? This current is going to also produce a magnetic field. Which direction is the magnetic field produced by this current that's induced? Is it into the plane of the board or out of the plane of the board?
It depends on where we measure it, right?
Well, let's say I'm talking about inside the circuit.
It'll be out of the plane.
It'll be out of the plane, right? As the rod moves to the right, is the flux increasing? The answer is yes, because the area is getting bigger. But the induced current is the induced current produces a magnetic field in the opposite direction, so it's trying to oppose that increasing flux. That's what that means. It's basically producing a magnetic field in the opposite direction so that it opposes the change in flux. If this rod were going, if I gave a push of this rod in the other direction, the flux would be decreasing and the induced current would be in the opposite direction. Because the system wants to maintain the flux. Okay? The induced current opposes the change in flux. I even showed that with the problem I did with the solenoid the other day. So what if the velocity of the rod was not was not perpendicular to the magnetic field, as it was in my case. Well, how did I calculate? Where did this BLV come from? Well, it came from applying V cross B. And I integrated over the rod. So this is the motional EMF. And I just integrated over a path. Okay. And so in general, you can write the motional EMF this way. If V is not perpendicular to B, I have to figure out what the cross product is in detail. Otherwise, the cross product is easy if V and B are perpendicular to each other. Okay. And so the change in flux then, the time rate of change in flux could really be written in terms of two terms, the induced one and the motional one. So we have two sources of a magnetically induced EMF, which is kind of unusual in physics. You have two really explanations that can occur for the same phenomenon. So if we write this all out, let me use a different color. So I've written Faraday's law in this manner. Okay. Oops, I forgot something. Okay, sorry about that. One can use vector calculus and rewrite this. If you use vector calculus and rewrite this, I'm not going to prove it to you, okay? You get the following expression. And that's equal to this stuff. Now, this is the same as this. Okay, so these two cancel out. And this shows that the integral of E motional, induced, dot ds is equal to minus the integral of the partial of B with respect to t So the induced EMF, the induced electric field depends on the time rate of change of the magnetic field. Which means, so if you have a time varying magnetic field, you're going to induce an EMF that's non-conservative. So this thing is non-conservative. Okay. So out of all this, if you're going to have an electromagnetic wave traveling through space, you have to have a time varying magnetic field. If the circuit is changing, the electric field that's induced is really more of a conservative field. Okay. Even in the motion, if you look at the motion of the rod on the rails, the induced voltage produced, or the induced field was conservative. Okay. And that one doesn't travel through space. It's this one that travels through space. It's this one that doesn't require a circuit to exist. Okay. So we've broken up Faraday's law really into two parts. One involving a changing circuit and one involving a changing magnetic field. So we have a better understanding of what that means. Now, if we want to apply all this to the rod problem, what do we get? In the case of the rod, this term is 0.
Zero because we said the field is uniform.
The field is uniform. Well, it's not only, it's uniform and time independent. So let's say the rod's going that way. We want to calculate the induced EMF. B and N, I'm going to choose N parallel in the same direction as the magnetic field. So this dot product is 1. What's my dA? Well, it's going to be, let's see, this distance times my dx. Because my area is increasing in the x direction. But isn't dx via the rod dt? And the answer is yes. And so this is equal to minus d over dt times the integral of b v rod dt. So what's the derivative of the integral? Oh, I forgot the L. If I take the derivative of the integral, don't I just get the integrand? Because this is a total derivative. Basically, it's B times the time rate of change of the area. Okay. So to summarize what I've done so far, you can have an EMF arising from a moving circuit or a circuit that's changing its shape, or one that's induced due to changing magnetic field. So in the second case, the induced EMF, the induced electric field exists even if there's no circuit present. The only thing that the circuit does is allow the electrons to move in the wire when you put the circuit in the presence of the induced electric field. Okay. Suppose we have an airplane moving at constant speed in a uniform magnetic field that is perpendicular to the plane's velocity. Is the flux changing across its wings? The answer is no. Right? If you have an airplane here's a region where you have a uniform magnetic field. Those are the wings of the airplane going, let's say the airplane's going that way. There is no change in flux. And as a result, there is no current induced on the surface of the plane. Will there be an EMF induced on the plane, on the wings? Yeah, there will be. Okay? But there won't be a current induced. There's no changing flux. What will happen is the charge will separate, and once they separate it, that's it. You'll have positive charge here, negative charge here using the right-hand rule. You will have an induced EMF, but there's no changing flux. There's not going to be any current induced. If you have a loop of wire of fixed geometry moving at constant speed in a uniform magnetic field that's perpendicular to the loop, is the flux changing through the loop? Well, we got to be careful. How's the loop arranged? So let me draw, I'm going to draw you two loops. This one and this one. Both loops move to the right. Is there a flux changing through this loop?
Neither the field nor the area is changing, so no.
Okay, so there's no flux change through the loops. But is there an EMF induced? It turns out there's an EMF induced on this rod, on this leg of the rectangle, and on this leg of the rectangle. Since the induced EMFs are the same on this one and this one, there's not going to be any current going through there. Okay. So you're not going to have any current going through there, even though you have an EMF here and an EMF here. The total is going to be zero anyway. So there won't be any current. But what about this one?
We're saying the field is defined only where the x's are?
Yeah, they stop here.
Okay, so it goes through a changing field.
There's a changing field, so the flux is changing, right? And so you'll have an induced EMF here, but you won't have one here, right? This is like the bar on the rail problems. And so you have a potential difference between these two ends that means that current's going to go through the circuit. The current's going to go this way. Your flux is increasing. This is the same as the bar and the rail problem. Okay. Suppose we have a current carrying wire. Maybe let me make this bigger. We have a current carrying wire, as you see there. Let's let the current in the green wire increase. What is the direction of the induced current? I have a green wire. I'm going to use green, but this is not going to show up very well. This marker's dead. I'm going to use purple for the green wire. And let me draw my circuit above it. I draw a resistor there just to represent the total resistance of the circuit. So the current is to the left. The current is increasing, which means that the magnetic field is increasing. What does that say about the induced current? What is the induced current in this example? Well, let's see. This wire produces, doesn't it produce a magnetic field into the, isn't the magnetic field here into the board? Isn't that true? Now, it's not uniform around the loop, but that I understand that. But it's true that the flux is increasing into the board, correct? The induced current wants to oppose that increase in flux that's into the board. So induced current is going to produce a magnetic field out of the board to oppose the increase in flux. And so I induced is this way. We're okay with that?
Barely.
Barely? What is it that's hard to
Oh,
understand?
no, I think I get that. It's just this entire unit is much more difficult for me to grasp than everything else has been. But I do see the balancing
Okay.
the opposition fields.
Yeah, this is not an easy unit, that's true. And more of the problems, in this particular chapter, more of the problems are more conceptual and mathematical just because they're hard to deal with. The math is hard to deal with. And I think as you do some homework problems, it'll get a little bit better. There's a demo that we do, which I can't do here. Imagine, see if I can make this bigger. Imagine a coil wrapped around a piece of iron. And at the top there's a ring. It's a metal ring that sits, as you see in the figure, that red thing. What happens when I close a switch and power up the coil that goes around the iron core? Well, we're going to have a changing flux. That changing flux is going to induce a current in that red ring. It's going to produce, the current in the red ring is going to produce a magnetic field opposing the one due to the electromagnet. And what will happen, if the magnetic field is strong enough, the ring will fly off the magnet. So I usually do this demo in class when people are here. And I show them how the magnet, I just show them the loop of wire, the little ring flies off the magnet and it hits the ceiling of the lecture hall. If I take the ring and cut it, as you see there, I increase the resistance of my loop, making it a lot harder for the electrons to flow. I actually get almost no induced current. And so if I cut the ring like you see there, there'll be very little induced current in the loop, and so the ring won't jump off very much. The current that's induced in that ring is called an eddy current. And both of those examples that you saw involved eddy currents. In motors, they're not wanted. And they're also not wanted in transformers because they dissipate heat. So if you have a transformer, which is basically two coils of wire with iron wrapped around them, since the iron is experiencing the changing flux, there's going to be a current in the iron core of the transformer. And so energy is going to be taken away just by the core of the transformer because of the eddy current. And what designers of transformers do is they actually take the iron core and they slice it, and they laminate it, they slice it into thin pieces and then glue them together. That increases the resistance and reduces I, and reduces I squared R. Okay. So I want to give you an example of an eddy current. So let me show you. My demo here. I only have one demo today. I have here I hope you can see it. Can't see it right now. I have a magnet, okay, and this is aluminum. This is an aluminum plate. And then put it in between the poles of the magnet. You can see that they're not attracted, okay? What I'm going to do is put this in between the poles of the magnet. I'm going to let this swing. Oops, that's not good. Sorry. Did you notice how it stops? How the magnet stops? The aluminum, can you guys see that okay?
Yeah.
Okay. You see how the aluminum gets stopped by the magnetic field? It's because the aluminum is experiencing a changing magnetic field, a changing flux, and there's a current induced in the plane of the this little paddle here, which opposes the changing flux, and it slows this down. Does anybody have an electric car? An electric car, they have regenerative brakes. And so when you hit the brakes, you're actually charging a battery. As it charges the battery, you're slowing down the car. Using this same idea here. Now what happens if I change my geometry of the aluminum plate? Now what I've done here is I've increased the resistance. So it's harder for current to flow, or harder for charge to flow. So it takes longer for this to come to a stop. It still comes to a stop, it takes longer. I mean, compare that to this. Oops. Just by cutting slots in here like this, they made a difference. Those eddy currents were significant in this little piece of aluminum that would stop it. So you can have eddy currents that are useful for you, like for brakes, or eddy currents that are not wanted. For example, as in transformers. Okay, let me fix the camera. Take a look at this system. You have a ring on a table, and on top of the ring, lying along the diameter of the ring, is a wire. And the current in the wire is to the left. Let's say we increase the current in the wire. What can you say about the direction of the current that's induced in the loop? Maybe venture to guess.
Would it be 0?
Why do you say 0?
Well, if I separate the loop into like a top and a bottom half, and I know that the current is flowing, the induced current is flowing opposite the direction of the current in the wire, then they would both be moving towards the right, where there's nowhere to go. They'd be in opposition of each other. The current in the two half loops.
Yeah, I mean, yeah, you're right. I mean, this is how I would look at it. What's the flux through that loop? In other words, what is the magnetic field? What is the direction of the magnetic field below the loop? What is the direction?
Out of the page.
What is above it?
In.
And the areas are the same, right?
Yeah.
So the total flux is always 0. So I would look at it, I mean, I could look at it that way. And since the flux is always 0, regardless of how I changes, then there's not going to be any induced EMF. Okay, so let's do one more example. Well, I actually have several more examples, but one more on induced currents. This is an important one. This is a common one that you'll see in, this is one of the few you can do. Okay, there's not a lot you can do mathematically. So, just 1 second. We have a current carrying wire and a loop of wire below it, and we want to determine the induced EMF in that loop. Let me draw a picture. It's the same geometry as the problem where we find the force on the wire on the loop, but this is the different problem. So I want to find d phi dt through this loop. Okay, so what is phi, first of all? What is B in this case? Well, here's an issue here. B varies along here. It has the same value along any horizontal strip a distance y away. So anywhere along this strip, the magnetic field is the same. And we can make this strip thickness dy. Its length is L. So anywhere along here, the magnetic field is the same. So my area that I'm going to use is the area of this strip, because I know B anywhere along here has the same value. So my dA is going to be L dy. This is the magnetic field due to a long wire. The magnetic field is, point my fingers in the direction of current, my fingers curl into the board, the magnetic field's into the board. So I'm going to choose N into the board. Okay. So then my integral is this. So I'm going to integrate from d to d plus a. Now, the induced EMF is minus d phi, so B dt. I just want the absolute value of this thing. I don't care about the signs for now. The minus sign is just going to give me the direction of the current. Okay? And so I want to take the time derivative of this thing. And the only thing that's going to change here is the current. Okay, that's my induced EMF. If you want to calculate the induced electric field, that would be a tough problem, and the reason why is because the magnetic field is not uniform. Since the magnetic field is not uniform, the induced electric field would not be uniform. So that would be a tough problem, very difficult problem to do. Questions on this?
You have a Y that stayed in your. Oh, okay, never mind.
Oh, no. That's a mistake. Thank you. That's me spacing out. All right, thank you. Sorry about that. Other questions? Okay. Let's go back to the wire on the rail problem. I want to know what happens to the velocity of the rod. I just give it a push, okay? What happens to the velocity of the rod? Can I derive an equation for v as a function of time? Of course I can. Otherwise I wouldn't ask that question. Let's go ahead and set this up and do it. And it's really not that bad. So the field's into the board like before. Okay. And we know that the current that's induced is this way. We know that the force that's produced by this current is to the left. So let's do the following. Let's pretend the only force acting on this rod is this. There's no friction in the rails. Okay. By the way, I'm also ignoring something called self-inductance, which we'll talk about in the next chapter. Okay, so I want to sum the forces on this rod. And what is the force going to be? It's to the left. But my I here is my induced EMF over R. And this becomes so that's my force. And this has got to be equal to the mass of the rod times the acceleration of the rod. But the acceleration of the rod is just dv dt. And then let me put the m on the other side. I will put everything with v on one side and everything with t on the other. like that. In fact, let me rearrange things a little bit more. I'm going to put these two terms up here. When I integrate, I get that. Then exponentiate both sides. You guys still can see this?
Yeah.
Okay. This is a constant, is e to the c. So maybe I'll just call it something else. What is this constant of integration? Well, it's really, if it's the velocity of the rod when I started. So let V of the rod be called V initial at t equals 0. So V rod is V initial e to the minus b squared L squared t over mr. And so the velocity decays exponentially.
Is it not e to the v naught because the whole thing was a constant? Because you had e to the c, right? And c would be...
Oh, you mean this thing? Oh, you mean, you're talking about this guy?
Yeah, that's what you replaced with k, correct?
Yeah. That's because it's just a constant. I used to call it c. I used to write e to the c as c because I don't care what the value is, but students didn't like that, so I changed it to e to the k, or I changed e to the c to k.
But then you change k to v naught, correct?
Yeah, because I said, okay, what is this number?
But why is c not v naught?
Why is c what?
Why is c the value of when you took the integral and you got your value plus c?
That's the
Isn't
constant.
that v naught?
Oh, why isn't it v naught?
Yeah, I was just curious because I thought that it would be e to the v naught, not just v naught. If that makes sense.
I mean, I didn't decide to. I did not decide to apply my constant of integration here. That's all.
Okay.
I mean, I could have. You're right. I could have done it here, right? I would have said, oh, when t equals 0, what is this? Well, it's got to be. This has got to be the log of v initial. I could have done that.
Oh, I see. Okay.
Okay. I just chose to do it a different time.
Got it.
And maybe I should have done that. Okay. I'm going to wait to do the next problem. The next problem is really a rail gun. It's like a rail gun problem. I just want to talk about some applications. Maybe I might go back to that problem on Wednesday if we have time, or if I get to it today, we'll see. So there's some applications of Faraday's law. Coin mechanism, vending machine, SIDS monitor, magnetic recording. Oh, that's not used anymore. The induction heating on stoves. There's a lot of applications. Here's one: the electric guitar pickup coil. You pluck the guitar string, which is magnetized because it's near a magnet, and the magnetized guitar string is vibrating, producing a changing flux as observed by the pickup coil. So there's an induced EMF in the pickup coil, it's amplified, and then the signal's processed. Suppose you take a loop of wire in a magnetic field and you rotate it. So whatever the area of the loop is, let's say we have a uniform magnetic field, and we rotate the loop of wire either about this axis or this axis. Okay? And let's say the magnetic field's in or out of the board. What happens? The magnetic field's not changing, but the angle between the normal to the loop and the magnetic field now is constantly changing. If I rotate this with an angular velocity omega, then the dot product of B dot N has to be written as B cosine omega t. Because omega t is the angle between the normal to the loop and the magnetic field. So imagine the magnetic field is in or out of the board, and this thing is rotating either this way or the other way. The angle between B and the normal to the surface is constantly varying, and is given by this expression. And so, what if I calculate then d phi dt? Well, since the magnetic field is constant, this integral is easy. What's the derivative? What's the derivative of the cosine?
Negative sign.
Sine, okay. So the induced voltage is BA sine omega t. Usually the loop has more than one turn. We have a loop with n turns. So really we need to multiply everything through by n. And so the induced voltage is given by this expression. Okay?
Professor?
Yeah.
Where did the omega come from before?
Okay, so I'll go
omega?
back. I'll go back and see. You see this picture?
Yeah.
So this is the rate at which you rotate the coil.
Yeah.
The angular velocity.
Yeah, but when you took your derivative, you got BA omega sine
But
omega
chain
t.
rule, right?
Oh, it's dt. Okay.
Right?
Yeah.
I got to use a chain rule. Okay. This is what comes out of your outlet. Okay? This is what comes out of your outlet. You take a coil, at the power plant, basically you have a coil of wire rotated in a magnetic field, essentially. Okay? And the energy is transmitted to your home. But this is what's out of your outlet. And so in your home, omega is 377 hertz. In your home, N times A times the equivalent is about 170 volts. And so what's coming in your house is 170 sine of 377 T. What I've just described to you is a generator, an AC generator. Here's a little AC generator. Wrong one. This one has a light bulb in it. Okay, there's no battery in this thing, okay, it's just a light bulb. And so, okay, let's see if I spin it fast enough. Are you able to see the light go on or not? It's kind of loose. Okay, there you go. Okay, so you saw the light go on?
Yeah.
Have you ever seen one of these on a bicycle? The old bicycles would have a little generator on them, like this. And what you would do is, to turn the light on, there would be a little device next to your back wheel. You would have it make contact with the back wheel so that it would cause this to rotate, and then the light would go on your bike. You'd be producing the energy for the bulb. Okay. So anyway, this is how a generator works. It's a motor running backwards. Okay, a generator is essentially a motor running backwards. That's how the energy is produced at the power plant. And transformers are used to help deliver the energy. They're stepped up. They step up the voltage because when they step up the voltage with transformers to hundreds of thousands of volts, the current decreases as a result of conservation of energy. And then when it gets close to your house, they step down the voltages with transformers. So with AC generators, once you hook up a load to an AC generator, then current flows. So let me show you my little AC generator I had in my hand. I can change the screen here. So this is a generator. It's an open circuit generator. Okay, this is an open circuit because there's nothing connected to it. The two ends are open, and it spins very easily. And normally when the students are in class, I pass these around so they get to play with it. But once I connect something to it, I connect a load to it like this light bulb, it actually gets harder to spin. Okay? And the reason why it gets harder to spin is because when I put the light bulb in there, I have a load. There's a current now running through that loop of wire. And when a current runs through this loop of wire in a magnetic field, there's a torque on it due to due to this, where mu, the magnitude is N, A, I, B. NAI, sorry. And so when I put the light bulb here into my circuit, I close the circuit, a torque is developed, and I can actually feel that it's harder to rotate this thing. Why? Because I'm delivering energy to the light bulb. So whatever I put in is going to the bulb. When I have an open circuit, the only thing I'm overcoming is, friction. And this thing spins easily. This spins a little bit harder because of the light bulb. So this will develop a counter torque. And a counter torque, if the loop has a nice geometry, is just going to be NAI cross B. Okay? Let me just finish off my examples. So AC and DC generators, they convert electrical energy, and they convert mechanical energy into electrical energy. They need to keep the charge flowing in the same direction. So for a DC generator, you use the split ring commutator. But a DC generator with the split ring commutator, it doesn't mean that the current's constant. The current's like this for DC. It just means it doesn't change directions. Okay? The voltage has the same form. That's an AC generator. Of course, you can run it as an AC motor too. All right, I just want to say couple more things, and then I'll be done. Suppose you have a motor and you turn it on. What is a motor? You have a loop of wire and a magnetic field. You're building one, right? You have a loop carrying current that's rotating in the magnetic field. As the motor starts up, the flux through that loop is changing. And as a result, as the motor turns, there is an induced EMF in the loop of the motor. We call that a back EMF. And so what happens is the total voltage on the coil in your motor is the power supply voltage minus the induced EMF. That reduces the current in your motor. So if you have a motor, an electric motor, the current in the motor is going to be whatever the power supply voltage is minus the induced EMF divided by the resistance of the coil. We'll call this the back EMF, which is determined from how fast this thing is turning. And so as this thing turns faster, then the induced EMF increases. And why does a drill overheat when you press too hard on it? It's because it's drawing too much current. When it runs at full speed, it's not drawing as much current, so it won't get as hot. All motors draw more current when they're starting up. So I have this real simple example. Suppose you have a motor that has a resistance of 4.1 ohms. Okay? You plug it in, your current is going to be 120 volts over 4.1 ohms, which ends up being like 29 amps. Okay, so I initial. When it's running, this motor, this particular motor, I got this out of a textbook, has a back EMF, which is huge, 118 volts. And so the total current when it's running it's just the difference between the power supply voltage minus the induced EMF, and this gives you about half an amp. Although it's not, most motors aren't that exaggerated. Okay, but I just wanted to show you this as an example. I took this out of a textbook. Okay? All right. So I'm going to do two examples. The one I skipped, and I want to do one more on Wednesday, and then I'm going to start the new chapter. There is, and I think I sent you an email regarding this, there is a video on displacement current. I want you to watch it. And I expect you guys to ask questions about it, because even though I'm not giving a full lecture on the displacement current, I want you to understand it. Okay? Questions?
Not about the material, but Isaiah, before he left, wanted to confirm that you would be on campus until 3:30 today?
Till 3.
Till 3, okay, thank
Yeah,
you.
because I have a meeting at 3:30. Other questions? Okay, that's it then. We'll see you on Wednesday.
Thank you.